So, there again we go back to that iterative convolution that we talked about. So, essentially you would have a situation where you first construct H 0, H 1, H 2, H 3 lying on So, the situation is that you need to compress and convolve, as we did in the Haar case as well. So, you would start essentially by putting H 0, H 1, H 2, H 3 like this. Then, now remember what we are doing here is to construct phi t, the scaling function or the so called father wavelet. If you recall, the basic step every time was first to take the sequence and then to take the sequence squeezed on the time axis by a factor of 2. So, if you put the sequence at these locations, now put the sequence at the following locations H 0, H 1, H 2, H 3. Here these two locations are midway between these two locations here. So, midway between this is this and midway between these is this, and put H 0, H 1, H 2, H 3 here. Visualize these to be impulses of strength H 0, H 1, H 2, H 3, and here again impulses located at these places again with strengths H 0, H 1, H 2, H 3, and convolve this with this essentially. So, it is an iterative convolution, and you can visualize that you would get impulses in one step of this convolution. From 4 you would get 8, and in fact, this would stretch a little beyond, as you can see. In the next one you would again get this squeezed by a factor of 2. Now, in this case it is much more difficult to visualize where this convolution is leading. What I have given you is the mechanism, and in fact, it is a very important exercise, a simple, but a very effective computer exercise in this course to actually carry out this convolution. What kind of a phi t would result? The answer is not trivial. So, it is unlike the Haar case, where you had a very neat answer. You got a nice beautiful rectangular pulse of height 1. That is not the case here. The impulse response coefficients are somewhat complicated, and when we start convolving them, you have 4 of them, you are convolving 4 with 4 squeezed by a factor of 2, and this is going to go on. What you can see, of course, is that ultimately all these impulses are going to come over a finite area. That is a point of observation. I want to explain this point to you. It is a subtle point, but not very difficult to understand. You see, let me go back to this drawing. The first time you carry out this convolution, this with this, you are going to have an extension of the length over which these impulses lie. So, after this step, you can visualize H 0 coming here. So, the spread would be up to 3 of these samples going beyond H 3. The next time, you would have half of this interval getting added on there. So, if I call this interval L, then you have the interval L by 2 here. So, let me draw the situation carefully. Let me draw it for 2 or 3 steps. So, what I am saying is, it is a convolution something like this. You start with a train of impulses which is spread over a length of L. The next time the same train is squeezed by a factor of 2. So, it spreads over an interval of L by 2. The next time it is squeezed again by a factor of 2. So, I will draw them squeezed together like this, and this length is L by 4. And when you convolve this length L with length L by 2, you get at this stage length L plus L by 2. And when you convolve this with this, you would get L plus L by 2 plus L by 4, and so on so forth. So, you can see that the length is not going to go to infinity, but it is going to converge. And what is it going to converge to? Very simple. As we carry out this iteration to infinity, the length is going to converge to L plus L by 2 plus L by 4 and so on. It is a geometric series, and the sum is very easy to calculate. It is 2 L. So, what we can see for sure is that this leads to what is called a compactly supported scaling function. When we iterate these impulses with a contraction every time, we ultimately get a function lying on a compactly supported region. Or a more accurate way of saying that is the function, the scaling function is compactly supported. It has a finite part of the time or the independent variable axis on which it is non-zero. This is such an important thing that we should write it down and we should emphasize it. We converge towards a compactly supported scaling function. And what does that mean? We are essentially saying the region, the independent variable region over which it is non-zero. So, I will continue this, over which the scaling function is non-zero. Is finite. Now, this is the most important contribution that Dobash made. Before Dobash introduced this set of filter banks, the idea of neatly constructing a family of compactly supported multi-resolution analysis was not existent in the literature. So, I would put this as a very, very powerful contribution. That does not mean that the seeds were not there. In fact, the subjects of wavelets and filter banks as a multi-rate signal processing paradigm had almost developed in parallel. But using filter banks in an effective way to construct compactly supported scaling functions and wavelets is an important contribution emerging out of Dobash work, the work of Dobashes. Not only just compact support, successive scaling functions here have some additional property in terms of their behavior with respect to polynomials, as you can see. For example, what would happen in the second member of the Dobash family? Let us reason it out a little better.